that I'm going to introduce him.
Bah oui, je dis.
I know. It's but I don't.
You're aware that Adriana as well on videos is.
Yes, I was.
Okay.
So I just.
I mean, I know that one at some point, but previously, conference. One of the videos that
Okay, yeah.
I will see. But the other video was, I used it in a conference before.
I think we're good. All right. So welcome to the final session, which I've called Visionaries here. Kind of work. These are presentations on research in animation, film, visual effects, and graphics from the various faculty members who are a part of this Create Vision program. So to start things off, we have Chris Jocelyn. So you would like to come up? Well, I mean, you don't have to come up.
Oh, okay.
I'm joking. So there you go, Chris.
Lovely. Thank you. Do I get my notes or no? No, okay.
Yeah, you can see the notes.
Oh, yeah. All right. Yeah. Oh, you changed it into a PDF. Did I? I didn't make it a PDF. Why is it a PDF? All right. All right, let's see if that works. Okay. All right. So I want to do this presentation. So actually, I maybe introduce myself if you don't know. So I'm the co-director of this project along with Leslie. And one of the things we did with this project, or one of the reasons we started this project, was because we realized that there was, to some degree, I don't want to say a lack of innovation, but there's definitely a lot of innovation in the industry. But there's a lot of things which is still brute force. And so my student this morning, Leah, who presented her research, was for me a little bit of an inspiration for this project. She actually she took something we were discussing and about the subject and the ideas and the processes that are involved. And we realized that there wasn't a great process for this. And in fact, there was a lot of brute force actually happening. So I put together these slides kind of on that basis, in the fact that what people kind of expect versus what actually happens is kind of there's a bit of an offset, a bit of a difference. And so if you watched her presentation this morning, she was talking about facial motion capture, retargeting, and all these kind of things. And so in this respect, I'm actually talking about the promise of what that was and still is, and then the actual reality that is actually occurring. So I sort of put together a little bit of a brief history of facial motion capture. So for in terms of the actual papers and publications, not necessarily for the industry, we actually have sort of started around the 1990s. How long do I have, Leslie, by the way? Oh, shoot. All right, I got to cut this down. All right, so 1990, things happened. So around the 1990s, there was some early work, and specifically some work from Lance Williams published in SIGGRAPH in 1990. Some very basic facial animations, and this was actually done. This was actually a texture manipulation. So there's not actually the idea of sort of driving sort of vertices, but actually just sort of textures and manipulate textures to create a spatial animation. Same idea for Elizabeth Patterson's work in 91. And then we started to get sort of from Tzopoulos Dimitri Christopoulos, who was actually fairly big name in the industry. I think he's now retired. But at least when I was doing my PhD, he was a big name. He started creating more 3D work. Nadia Thalman, who actually did my PhD with, she also did a lot of work in sort of facial communication and facial synthesis and things like this. Very much her topic, and she actually used to be a professor at the University of Montreal, and then she moved to Geneva a little bit later on in the mid 1990s. And the same thing, there was a lot of ideas of driving faces and creating sort of the idea of having speech input and things like this, and then driving facial animations from that. Oopsie. Irfan Essa had published a couple of papers around roughly the same time, sort of being able to deform actual facial grids and being able to track faces and things like that. That was obviously a big thing. Now we're talking 1996, right? So 1993 was kind of Jurassic Park era, sort of the first Jurassic Park, obviously not the last one, but still the best. And that was sort of this sort of period of computer graphics, right? So Jurassic Park was fairly pioneering in that type of work. So really, in terms of facial animation or facial capture, we've got probably one of the ones that we think about most is probably Gollum from Lord of the Rings, played by Andy Serkis. But in fact, what they didn't actually do facial animation capture in Lord of the Rings. Serkis just sort of did the animations, he sat there, he did the motions, he did the acting, but they were just using that as reference. And then they had, a bunch of animators, I think 18 animators, sort of come along and replicate those motions for Gollum. The first, as far as I'm aware, animation using facial motion capture that was actually done was probably Polar Express with Tom Hanks. This, obviously had some fairly uncanny valley kind of situations going on, but it was, multiple characters there throughout the movie. Similarly for in Monster House, multiple characters done in that situation as well. And then we had sort of, movies following on pretty fast after that. If you've ever watched Spider-Man 3, you've got sort of the Flint Marko Sandman and Eddie Brock Venom having facial motion capture. For me, one of the most seminal moments in terms of facial motion capture where they started to get it kind of like almost right was sort of Beowulf. The whole movie was CG, but a lot of the characters looked almost exactly like their counterparts. So, Anthony Hopkins and Angelina Jolie were captured, facial animations were captured and then replicated in CG to be able to expand on that and be able to do different things that you wouldn't normally be able to see. One of the other ones was probably Avatar. That was extremely heavy in terms of obviously motion capture, but there was a lot of mix. There was still the idea that we had some actual real people, but then also mixed into the actual avatar bodies themselves as well. And then it sort of got better and further on from that. So you've got Rise of the Planet of the Apes, and obviously a lot of the stuff done in the MCU universe. So the idea behind this process, and I'm gonna sort of skip quite quickly through this, is that we have to take, when we're doing any type of motion capture, we have to take the motion data. So we're taking something recorded, or we're taking something that already pre-exists, and then we're converting it using retargeting, and then we output this to another face. And even if it's the same face, there's still, still a conversion process. We still have to process the parameters to be able to get something and move something at the other end. So basically we've got, and within reason, what I'm talking about is I'm talking about the fact that we're doing some type of motion capture from the face, from somebody's actual face, and then pushing it onto an actual character. So there's all sorts of problems that happen with this. There's obviously what is actually happening with the skin, what are the muscles doing? There's lots of muscle groups within the face. And, we use a lot of the facial animation cues to be able to understand what somebody's talking about. And if you want to know more, you have to come to my animation class. We talk a lot about how facial animation cues are very, very important, and how, one of the reasons that Disney uses big eyes and things like that is that they want people to be able to read those expressions from far away. But I won't get into that. Now, in order to capture that data, we're going to use obviously a marker or markerless space system, software such as Vicon Kara. I've been doing facial motion tracking using Vicon since 2006. But markers on the face, you can use software such as Faceware, which is actually a pretty big industry standard to capture that kind of data. And then we do some translation. All right, so let's start with the target. We have a target that we want to map to, and we usually set up the target first because that's the character or the person that we want to put into our movie, our animation, or whatever it is. And we can do it through lots of different methods, blend shapes, 3D morphable models, or joint based, or anything else like that. So there's lots of options for us to sort of retarget to. But one of the things you'll notice here is that we're not actually, taking something and just applying it directly. We have one of the bigger ways that we do this, especially nowadays in the industry, is to use blend shapes, right? And if you're familiar with blend shapes, that means that we're not actually taking the animation that we have and slapping on a new CG model without doing anything. We're actually having to set this thing up. So we're actually having to set up all of these models in advance to say which motions, which elements are moving, and how we want them to move, and how we want those vertices to move in general. So there's a lot of processing to go, to get that set up. And in fact, what we found when we were doing our investigation is, in order to get this to set up, you need something like 4 months to set up a character with all the blend shapes necessary to capture that facial animation. So a process, I'm shortcutting this a little bit. The process itself, which looks like you would be able to go up, take somebody's facial animation and apply it directly to a 3D 3D model, is actually a 4-month process of setting up all these blend shapes in order that you actually get all the expressions that you want, and then creating a mapping between the two. And that's pretty much industry standard. That's pretty much most houses are doing, for Avatar, for Rise of the Planet of the Apes, all these kind of things. And then you've kind of, as I said, you've kind of got this conversion process, which is your step 2, which is the retargeting, where you take the face, record it in the studio with all the markers or without all the markers, and you're transferring it and applying it to a new face. Could be the same, it could be the same dimensions, could be the same mesh as the original face, or it could be a new character, right? You've got Mark Ruffalo in the MC universe playing the Hulk. He doesn't look, his facial proportions are not exactly the same. There's a resemblance because it's supposed to be him, but overall, there's not a direct mapping. So you've got to have some kind of conversion. All right. So let's talk about the idea of what we kind of think we would like. So we're currently on, we're 35 years since the first development of this kind of idea of marker-based sort of tracking and applying to animation. So what we kind of think that we want to have, or should be at this point in time, is the fact we would think there would be no markers, right? That really, you wouldn't have to sit there with for ages putting on these markers and applying one by one, or drawing them on, or something like that, right? You should be coming to a studio, say, right, this is me, okay, act, and it's done. But we did, that's something else. We also don't expect to see a camera, right? We don't want to see a camera stuck to our face when we move around. That the camera itself should be unnoticed. And within reason, it should be real time. So we have something that we do the recording, and then we can apply almost immediately to a character, to a new character, and get all the nuances and details and expressions that were originally recorded. We also want any target, right? We want the character to be whatever we want it to be. We've created a new character, we've designed it, and we want it to be easily to apply. We don't want any time to set up that target. We don't want to have to spend that 4 months setting up that facial mesh ready to be animated. We want it to be ready to go, done. The other thing that we don't want is we don't have to edit. We want to get all the nuances and all the details from the actor on the first take, maybe the second take, and done. We don't want to have to edit. Editing is a pain. And you're also losing the details from it, right? Mark Ruffalo spent time in acting school, and now we have somebody editing afterwards and changing that. That's, you know, a little bit of a problem. So the reality is, right now, tracking markerless isn't great. All right. I actually have 2 USRA students over the summer who are helping me with this, but we're finding that the details and the nuances that are actually coming out of the markerless systems are pretty bad, right? There are spatial expressions you can do that they don't even have any idea what you're doing, which is, you know, pretty bad. If it's marker-based, you got to set up. You got to still take time. You've still got to do all the calibrations. The markers still fall off. And you know, they change your facial motion. If you've got a ton of markers on your face, you don't act exactly as you would expect in a normal point of time. Here's me in a marker suit, and I look cute. You also got things like markers being obscured by wrinkles and folds and you know, lip rolls and puckering and all this kind of stuff. So there's lots of things happening that we don't necessarily you know, not even taking account of. Cameras are still there. We still have lots of cameras. They typically sit in the front of the face and record the motions. It's very difficult to act. They're still heavy. So when you move your head, you still get the weight of the system moving around. Your data storage is still attached to you. It's a bit lighter now than it used to be. We used to carry on little packs of hard drives that would sit on your back. Now they're a little bit more like SD cards. There we go. Real time. Yeah, we've kind of got real time, but the quality isn't there. There's still some computation to do. The more quality you want, the heavier it is. Targets still need to be rigged. Regardless of the target, you still need to take the time to create blend shapes. If you're doing, as I said, a production quality system, you're still talking about something like 4 months, which is, you know, a lot of work. The last thing on my list here actually is editing, which I haven't mentioned, but most editing. So one of the things that I found very interesting is when we were doing our research, when they were doing the capture for the Hulk in the MCU universe, they would take the 4 months to set up the rig, and then they'd take another 2 months worth of editing, right? So Mark Ruffalo would do his thing, you know, all angry or sad or whatever it is the Hulk does at that day. And then they still have 2 months of post-editing to get all the details and correct all the motions that weren't captured properly in that kind of thing. And that's, you know, just most of it's spent just correcting an error. So I think that was very interesting in terms of the work that we're doing. And just to put a final note on this, we're really looking at, you know, ideas. I'm still, you know, Leah's work, if you saw Leah's presentation this morning, she's developed a new muscle-based system. She's using cloth on the face to act as skin. So it looks, I mean, to be honest, it looks really good. I think she's done a fantastic job. But there are the other areas that we can sort of start looking at, which might help a little bit. So speech and audio might help. Understanding what the person is actually saying would actually, you know, give some idea of what motions the person is going through. Muscle actuation. Her system is muscle based, so muscle actuation is very useful. Better motion analysis, being able to record and understand, and the range of things that people will do is very important to capturing better motion. One of the interesting motions that FaceWare is not able to do. Now, FaceWare is a industry standard, but we found out FaceWare is unable to capture this motion. Now, you might not do that very often, but it still can't capture it. I do that every day. just in case you're wondering. We were looking for face setups for various characters. You know, there's lots of things nowadays, especially what we're doing in the VFX industry. I think is very interesting because we've gone from, you know, dinosaurs to now having variety of characters that we want to, you know, fantasy type of characters, and then more and more crazy designs. And, you know, maybe to some degree, a larger number of cameras to capture facial events. So I don't know whether you know, but Vicon has now finally gone markerless. I don't know whether they're going to, you know, be able to capture the facial motion very well. But if you're buying a Vicon set of cameras, you're buying 20 cameras, 30 cameras, 40 cameras in a room. So within reason, you should be able to capture quite a lot of facial animation from that. If they're high enough resolution, you may get to a point those cameras get further away and we don't need them anymore. Anyway, so that's the end of my talk. Thank you very much. I hope you found it interesting. And was that 10 minutes, Leslie? No, very bad. 20 minutes? Well, 12 minutes. That wasn't bad. That was pretty good. All right. Thank you.
All right. So next,
Didn't have time for questions, right?
we'll do them at the end.
Okay.
All right. Next, we have Eric Paquette from ETS. And you open your.
I was afraid to run overtime, but now I'm done.
All right. I'm gonna like.
Well, at least you have a PowerPoint. You say,
Yeah. Yeah, it wasn't so clear that the PowerPoint would be converted into a PDF. Anyways, okay, so I'm Eric Paquette. I'm a faculty at ETS in Montreal, and I do my research in the multimedia lab, where we have a variety of expertise. And also advertisement, if you're a student giving my course, which is like inside this, the Vision Create. So if you want to take my course, it's on the Polygon Mesh Processing Thursday morning. If you see that, oh, it's going to conflict with Chris's course, we'll manage something so that there's no conflict. It's completely online. 3 quizzes, 1 project, examples of past projects, and the QR code is to get access to the syllabus if you're interested. Okay, so now it'll be like a speed run of many things I did over the past couple of years. Some of them are related to digital humans, but I'm also spread all over the place in computer graphics. So body reconstruction, so I did things around that. So here it was a work on, you have multiple input images and you want to reconstruct an avatar out of that. So we were using the simple body model, optimizing it to fit the input images. Then we went to, instead of having multiple input images, to having a single input image, and also reconstructing the texture for the avatar. So we did that with a more or less fancy pipeline, and then you can have your reasonably looking avatar, given that it's just one input image. And since we're using the simple body model, then it's super easy to animate the thing into your favorite 3D software. Also worked on faces. So that work was in collaboration with Ubisoft. So they captured a bunch of people, roughly 1,000 faces, and they wanted to do something with that. So we worked with 3D morphable face models to be able to capture, to interpolate and create new faces. We complemented that with anthropometric measurements so that you can edit with these measurements. And then, yeah, you can do some more or less interactive editing. So here you see modifying some of these anthropometric measurements. That's better. Good. All right. And then we went from 3D morphable face models to deep neural networks, kind of a bit like the same idea, but with deep neural networks, you're not limited to linear models, so that's definitely much better. So, and here we're able to conduct editing, so you kind of grab a vertex on the face, move it around, and then we back propagate to latent space and reconstruct a face out of that. I also worked on ears. So ears are particularly difficult because often there's hair around the ear. So with photogrammetry, it's like lots of noise, lots of crazy stuff. So we created an approach for that. And as you can see, we were reasonably successful in mapping our template ear to the input scan and removing the noise, but still being more or less faithful to the input ear geometry. Also worked on video dubbing, and also did a couple of things. So the idea is you have the original actor. In this case, it's Emmanuel Macron. He speaks French. You want him to speak the same thing in English. And we do that with a dubber. So the dubber narrates the text. And then from the dubber, we create a virtual dubber, and then we massage this thing to have something working well. Let's see if I get audio with it.
With this remaining because especially
Okay.
nowadays,
You can
this
see
is the time spent away from your loved ones, perhaps for years, because of the many restrictions imposed on travel around the world. I have a compassionate thought for our fellow citizens who lost a loved one without being at their side. You are aware of my commitment, and I will continue at any given opportunity to spend every effort to advocate and make.
Okay. So yeah, so you saw we were able to recreate something reasonable out of that. Good. So I worked on hair modeling as well. So in first work on braids. So recreating hair worked reasonably well, but for braids it was a bit more difficult. We kind of do some segmentation of these little chunks of the braid and reconstruct something. And out of that, we create a parametric model. So in the end, when you have the parametric model, you could make the braid wider, longer, with more subdivisions and so on. Also worked on creating guide hair out of a sculpted mesh. So for artists, it's easy to use ZBrush to sculpt a mesh of the target hairstyle they want, but to do the same with laying guide hair on the head of the 3D character, it's a pain for them. So then we analyze the mesh, extract reasonable curves, retarget the curves to the target head, because maybe you want to sculpt one hairstyle and retarget it to multiple characters in your VFX or a video game, whatever. And here you can see that it works reasonably well for short hair, long hair, etc. And you can see here the clipping of the head with the sculpted hair, and then you can see our retargeting, like the guide hair that we have there, they're retargeted correctly to the target head. All right, neural clot animation. So the goal here is to get rid of the simulator, do something good and close to real time. So the idea here was to use a good deep neural network method. So that's the top one, but that's graph neural network. So it's slow. So we use some form of the knowledge distillation. That's the middle part that we train based on the latent space of the thing at the top. And then later, the bottom row, that's the inference. And then it's reasonably real time. And we can do multiple bodies as well. So if you change the body shape, then you don't need to retrain. And yeah, the reasonable animation out of that. Also worked on the fluid simulation. So the idea here was to run something low resolution. And why do you want to do it low resolution? Because you can have a quick turnaround time. Because in let's say you're an artist doing this, if it takes a full day to simulate your thing, and you say, "Oh, I see it. It's not what I want." You go back. It takes too long. So if it's coarse resolution, then you're good. So created an approach for that. And oops. Okay, maybe you won't see it. Doesn't want to play. I thought we were past codec problems. Maybe not. Okay, anyways. And we have user control, so you can have splashes to splash more or less, even though it's not physically correct. It still looks good and it gives you more freedom to control your stuff. And we did the same now with deep neural networks. So you have like a data set of things that splash, and out of that, you, oh, okay, no video again. Okay, so you have to trust me or visit my website to see the video. Sorry about that. Texture synthesis on the deforming surfaces of liquids. So yes, we have like these little patches that we lay on the liquid. We move them around with the flow of liquid, and we blend them together and so on. And you can see here on with lava does something quite reasonable. Surface mapping. So there are many methods to compute a surface mapping between two objects, like point-to-point registration of these the two surfaces. Often these methods, they work quite well, but in some cases they fail lamentably. So here you can see with the head region, the matching is bad. So we derived the method to just edit the part that is bad and keep the part that works well. So that's kind of the idea. So we really segment the culprit region and massage it and reproject that to 3D to have like a good surface mapping. All right, so again, syllabus of the course. Oh, there's the okay, there you go. Syllabus, if you want to have a look. Current research that I'm doing, 3D Gaussian splatting, continuing on neural cloud animation and texture synthesis, and I'll also do a bit of CAD and fabrication. There you go. That's it. Thank you so much.
All right, thank you, Eric. Next, we have Adrian Gerson, also from ETS.
Yeah. Thanks. Check. Okay. Ideal. So here I represent one type of my work here that is like how we can use in-line transport simulation deep learning. So just because maybe not everybody know what is light transport simulation, just to have a very high overview about this, like basically you have as input like, 3D scene that is composed of some geometry, material, texture, light, and so on. This is your input, and then you have this nice function that is like how the light interact with this 3D scene to get photorealistic images here. Right. And this function, like you can see, that takes the 3D scene, but also some parameter of the algorithm that controls the output, basically, of this algorithm. And basically, this function f is very, very complex, like super expensive to evaluate, and so on. So usually how we do it is like we do a stochastic evaluation about this, meaning that retrace some light path, like we simulate these photons, how they diffuse inside the 3D scenes. And with enough compute, usually we can get a good image at the end. Of course, now these days, you can see like this is like light transport try to be replaced by deep learning in the sense that they try to learn this function f directly. And one thing that deep learning does is like sometimes they change the input, like it can be text prompts, so like it's just like text based and then you generate. So this is like Sora and OpenAI on someone that do a technical presentation on light transport in a university room. Or maybe there is also now these days more modern techniques that still take the same input as a light transport algorithm, but like have this kind of complex machine learning to generate an image. But one of the things that I will argue about these methods is like they are usually quite difficult to control, like the data set or the training cost that was already discussed during the panel is a problem, maybe the generalization. And one thing that is also quite important for some studios is like this tool doesn't fit really well with the legacy pipeline, like of artists are used to work and produce assets. So my research is more about light transform with deep learning. And what I mean by that is like we replace some part of the pipeline with some neural representation. So maybe, for example, I will not have classical material, but I might have neural material. So now we can evaluate this material, but we don't change the underlying algorithm, the rendering algorithm. So we still have some kind of the property of the rendering algorithm kept. Or maybe I can use a neural network for parameterize my rendering algorithm to get the best performance as possible. And basically, I will argue that this way, but making smaller neural network fitting in the pipeline is a better way to keep the control of your content. And the good thing about this is also like quite compatible with actual pipeline. And another property that is very difficult to do with basically like previous methods that I mentioned is like physical accuracy. Like you cannot ensure that you get physical accurate model at the end or image. So I will give you a concrete example. So this is a work published at EGSR last year by Ishan and a few of my colleagues. And I will frame it as a neural material. And I will tell you why it's interesting to look at this model in this context. So glint material, basically, so it was a work that we focused on glint material. So glint material is spatial material that reflect light with high frequency response. So when you move the light, you get very different results. And it's also coherent in terms of the spatial varying response. And another challenge on this thing is like the multi-scale appearance. So when you can zoom on the surface, you can see individual structure, but then you can zoom out and also see the aggregate appearance. So it's quite challenging to render this stuff because basically at each pixel, you look at thin detailed structure and you try to find good facets that are well oriented that you reflect the light. And it's just like trying and search randomly, it will never converge basically. So for this kind of challenges, basically, usually we design spatial rendering algorithm and legacy methods. Usually they take a patch of surface of your whole surface that you want to take care, and then they will transform it in a more compact way that we can make the search feasible. So for example, these BNet PNDF methods, basically they take all these small facet orientation, and then they will just express it as a histogram that tell you at this direction of facet, you have this number of facets that is distributed. And also the roughness that is material associated to the facet. And the good thing about these techniques is like it's quite efficient. Like if you have histogram, you have a compressed representation, you can do this fancy summit area table, and then you can get for every surface, patch surface, your histogram. Great, problem solved? Not quite, because these methods that are specialized, so you get very fast rendering. For a 2K by 2K image, you have almost 5 GB of memory. usage. So it's not feasible for any studio or any asset that will use larger texture or multiple texture to use that. So basically in this research, what we do is like we replace this expensive, memory intensive aspect with a neural network. So I will not enter into the details because it's not super relevant for the talk, but we optimize the texture plus MLP to just predict this histogram for a given position and patch of texture. And the good thing about these neural things now these days is like they are quite good for compression information or for some interpolation. So you can just reduce the resolution of your texture or your latent texture, use other encoding, and then you win a lot about the space. So like with this method, usually you can go to 50 megabytes of memory. And for the cost, here, this is the result. So at the top, you can see what is the original methods does with 4.6 gigabytes. And at the bottom, you can see what this neural methods does. And what you can see is like the image doesn't change a lot. And the black thing, like the black part of the image here at the bottom is just the error. So means like if it's black, like the error is not noticeable. So this is interesting because like you reduce the memory, but at the same time, as we use neural network, we are able to speed the rendering process. So we also win in terms of computational time. And I will argue with these methods, as we use traditional pipeline, I mean, we can now edit our mesh as we are used to. So here we move the texture parameterization of those objects, and then we can also edit the roughness. And this is like without retraining, like it's perfect control and incorporated in the rendering pipeline. So this is another example about this thing. Is like as we use classical rendering techniques, like it's temporally stable with these methods, and you can also keep this property of like multi-scale appearance, so you can zoom in the image again without any like temporal flickering or some stuff like this that you can see in the other neural methods if you just predict the image directly. This is one of the examples. Justin this morning presented another method that here was doing this usage of deep neural network for parameterization of the algorithm for photon mapping. As I think I spent a bit of time here, I will just skip it. If you are interested, just watch the video at the morning. So in conclusion, basically, for my research on this kind of topic, what I mean is like neural methods can make light transport more efficient by, compacting the representation or use the regularity or like the structure of the data to have a more precise representation as well, or expressive representation. It can also adapt the local context. So like having algorithms that adapt to what's happening in all the surfaces in the scene is very challenging to do it with classical methods, but neural methods can do it. And another advantage that is usually not very looked at is like neural methods with the push with NVIDIA and all these vendors have been now very well optimized for hardware acceleration. So like you can get an uplift on that. And the thing is like, the important thing is like doing so with neural methods while preserving artistic control and physical accuracy. So if you want to have more information about my research or recruitment process, you can see the QR code or going to the website. Thank you.
Thank you, Adrian. We now have a presentation happening remotely. Parmit, are you ready?
Yes, I'll just share my screen.
All right, so we have Parmit Tilana from Simon Fraser University.
So can you see my slides?
Yep.
Not the notes, right? Okay. Okay, perfect. Hi, everyone. I'm Parmeet Chalana. I'm an associate professor at SFU. It's been really nice to hear all of the different presentations today and attend the panel sessions. I think it's super interesting. So I bring in a slightly different perspective along with Sheila Carpendale, who's also part of this project. So our field is human-computer interaction. And, we build novel systems and techniques, but we're sort of doing more interdisciplinary research. We're also borrowing, theories from cognitive psychology, design and art, social and organizational psychology to, with this goal of improving user interaction with different kinds of complex, feature-rich software. And particularly for me, I also draw upon theories from education and learning sciences. I'm really interested in how people onboard new complex software. How do we understand the challenges that they face, what kind of user frustrations they face at the UI level, and how do we build novel techniques to alleviate some of those frustrations. So when we talk about feature-rich software, right, it can include lots of things, everything from the kinds of work that we do in this visual design sort of space with 3D modeling tools, design tools. It could even be spreadsheets, programming IDEs, statistical analysis tools. So anything where you have lots of complex decisions that you have to make. So these tools, offer a lot of features and functionality, but they're also, kind of are hard to use and troubleshoot, especially, as they grow in the number of options that they offer. Users can actually face a lot of complexity. And it's not a new problem. We've seen this back in the day, like this was your canonical knowledge worker sitting in front of a desktop computer. But the onus was always on them to adapt and learn these complex features and functionality on their own. And back in the day, you were given a user manual. So, if you were trying to do something in PowerPoint or Microsoft Word, you would have to look it up in the index to find, the exact problem that you were facing, or how do you, get instructions for doing a task. But you can imagine these things became outdated fairly quickly because, it's not a very natural way in how we learn and use software. So today, there's many more ways to learn and seek help. Help started being embedded right inside the application, so you can have more of a keyword search approach. And when Google came about, right, you could actually look up all kinds of information, including like videos and text-based tutorials and forums. You can connect with other people. But as we're seeing there's different kinds of usage contexts that are emerging, new types of devices, new types of application. There's also many types of software users that are emerging also, right? But the help tends to be provided in the same way. So, the question that we've been asking in our research is, how can we do better? How can we better support software users' learning and help seeking needs so that they can get over this hump and actually do better creative work or be more productive in whatever context that they're working in? So a number of my research contributions in this space have been both in empirically studying people and their activities, their workflows across many different domains, both in the lab and in the field, and also building new types of interactive systems and techniques. And then often we take these techniques back into the field and test them out with real people and see how it sort of fits in with their needs and so forth. So a lot of my work has looked at diversity in software help seeking learning. So some of my earlier work actually focused on 3D modeling and 3D design tools, and we're revamping some of this stuff now in the age of AI. What do all of our previous findings actually mean? We've done stuff with helping end user programmers who are not trained in computer science. How do they approach the coding process? We also build some tools and techniques for teachers in the classroom, kind of empowering them to use more complex like learning management systems. We've also done stuff with augmented and virtual reality authoring, so building interfaces that simplify the process for novices. And at a PhD student whose whole dissertation focused on motion graphics and video editing and kind of lowering the barrier for animating objects for people who are not professionally trained. So I won't get a chance to talk about all of these today, but I wanted to kind of touch on what are some of the common themes that you've observed across these various projects. And one of the key insights I wanted to share actually is really what we see is how users across these different studies have shown like they vary a lot in how they access different help resources and how they navigate between the application. So what I mean is here's a concrete example from somebody trying to find help from a 3D modeling study. We were trying to look at their design process and how we made it pretty open to them, like they could use any resource that they want. And this was before ChatGPT and stuff. This was done 5 years ago. So, they could start, we observed many different patterns in our paper. We kind of document this. So they would begin with a search engine, perhaps go watch a video, follow a text tutorial, go to a forum. So they were doing a lot of random things, not sticking to any one thing in particular. And again, we've seen this with study with programmers. We saw this with study with teachers, also a really wide range of patterns that people have. But it's fairly chaotic and they're not actually able to complete the task even after going through all of this stuff. They feel like they're disconnected from the actual task. They can't always locate what they want. They often don't have the appropriate vocabulary. And they don't, even if they find something relevant, they don't actually know how to map it back into the application. So, in terms of addressing this, and there's more studies that we've done in this space. Again, I'm like only giving a high level overview, but the flip side of that is, okay, given the problems that people face with current types of resources and the challenges that they face in actually retrieving relevant help, what if we design ways to help them retrieve relevant instructions in the context of their tasks without ever having to leave the application and minimize that vocabulary burden that they face to describe something, externally? So a lot of my other side of my research has, over the last 10, 15 years, we've looked at different ways of inventing novel interactive help systems and techniques. And again, I won't get a chance to talk about all of them, but I'll show you one theme of our work has really focused on in-application help retrieval. And within that, one flavor that we've explored is how do you not only provide help where people need it, but also allow people to connect with each other in the context of their tasks. So back in the day when I was doing my dissertation work, like crowdsourcing and community-based systems were becoming very popular. So I used that approach to build this tool called Lemonade, that I'll show in a second. It invented a novel way for users to find relevant Q&A asked by other users within the context of the application, simply by making selections in the user interface. So they didn't have to leave the context at all. They didn't have to go search randomly. And they could, this little demo that I have. So we had one of our deployments done at the University of Washington where I did this work. So Lemonade was deployed on the library website. So you click on help, it kind of changes the mode of the application. You see certain things highlighted. Again, click on it, click on some location that I think is relevant to me. And immediately I can see Q&A asked by other users at that location. So this kind of, provided a different visual reference, provided a nice sort of coupling of help needs. And we saw this like it was tightly held across different application UI. So even though there was a lot of variation when people were typing in natural language queries, when we asked them to point at something, there was a nice sort of convergence in similar parts of the interface. So we could like leverage that finding and have help like sort of embedded in areas where we knew the next user would also be looking. And the way I built it was fairly lightweight, and it actually became a product. We went through this whole process of taking this sort of lab-based product or lab-based research prototype, and because it was so effective at helping people, and it could be built on top of any website, we had a chance to sort of explore the commercialization of it, and it became a product, and it got bought out by this company called CloudEngage. Now they're doing all kinds of AI things with it as well. But the fundamental idea of doing the selection-based crowdsource retrieval, became fairly popular and got adapted in many different ways. But the way we did this was it was more asynchronous. So it was really dependent on community contributions. And sometimes when you're in the middle of your task, you need more immediate feedback. And for that, we explored a different project, which we called Marmalade, and this was led by my student, Nathaniel Hudson. So where this allowed users to share their work in progress, establish a shared visual context, and then initiate more real-time one-on-one conversations. And we actually did it for a 3D modeling application that we built on our own. So here is somebody who's working on their model, and when they feel like they have a question, they can just click on the Q&A button, as you'll see in a second, and they can initiate a conversation at any part of the geometry of their model and get very targeted responses. They can connect with an expert. So it really reduced the number of words that they would actually have to write to explain their visual context, because the expert could see it right away. And Interestingly, we saw that people were having, multiple conversations, and they actually wanted to save this for the future as well. So this became like their own personal tutorial and personal help file. And, they didn't have to leave the workspace. They could just communicate with other people in real time and get the help that they need. So another aspect of this, so there's asynchronous Q&A, there's real-time Q&A, but sometimes in other contexts, we have found that people don't even care about the answer. They just want somebody else to do it for them, or they just want to grab something that other people had done because they don't have time, or they don't actually want to invest the technical knowledge in actually figuring out how something works. And we saw this especially in the context of teaching and learning tools. When instructors are really busy, they don't really actually want to sit there and understand how every single thing works. So we built, my student Leighton Vermette built another tool called Customizer, which allows users to actually still have that community aspect, so they can browse other professors and other instructors' courses and import their customized features. So, it was a little plugin that they can install, and we use the Canvas system at SFU. So we tried it on that, which is used actually very widely by 30 million people across the world. So here, there's a little plugin that's in my own local environment, but it allows me to connect to a community of instructors, and I can see the types of customizations other profs have done, and I can immediately try it out in my own environment or import it, and it would become functional in my own course. So these are some of the ideas that, we kind of tried, and now with LLMs and Gen AI, it's kind of pushing us to go in a different direction and to think about, okay, are all these other help systems obsolete? Can people just go to ChatGPT and, get all the answers that they want? It turns out it's not so easy. In some of our early work, we have done some empirical studies and designed our own co-pilots to test out these effects. So a lot of this is still kind of work in progress, and my student Anjali Khurana is leading these efforts. So I wanted to show one example here. We in one of our studies, we asked people to use ChatGPT in whatever way they wanted. We gave them a simple task to animate a shape in PowerPoint using very basic features. And one of the users wrote this prompt, right? He says, I want you to give me instructions on how to animate a shape that rotates from top to lower middle side and then comes back almost like a zigzag. So fairly, simple kind of thing. We saw lots of participants do this type of work. And ChatGPT gave a nice step-by-step instructions. But one of the instructions as part of that was, it says under the add animation option, select more motion paths at the bottom of the drop-down menu. A new window named motion path will pop up, scroll down and select the zigzag option and click OK. And this participant, there is no zigzag option, right? So it was hallucinating, not really giving the correct answer, but this participant spent the rest of the study looking for the zigzag option, and they wouldn't give up. They said, no, the AI said, there is a zigzag option, so I'm going to look for that. And it was very frustrating to watch. We didn't want to help them because we wanted to see what their natural behavior is. And in the end, they kind of gave us this really nice quote that it's, oh, because it's AI, how can it be wrong? So it just shows, people are putting in a lot of trust into these applications. There's a lot of overconfidence as well. Not so much of critical reflection of what is actually accurate or not. And it's impacting the way people form the mental model of the given application. So sometimes it can actually be very, very wrong. And, we haven't even kind of solved that issue yet. And, companies are putting forward even more co-pilots, more ways to automate tasks. And, they promise this one-click natural language way of automating workflow. So it makes us a little bit worried, and we are investigating right now what should really be the optimal level of optimization for designing an effective user experience, especially if you're going to embed them in these feature-rich type applications. And there is some recognition that, AI models are having difficulty, which is not surprising to me as an HCI researcher, but when they're saying there's complex, ambiguous tasks, maybe when they're not as structured, when they require coordination, they get messy, and then the models are sort of breaking down. And to me, that's a ripe opportunity for us to sort of, bring in more user-centered techniques, more of our findings from HCI to help mitigate some of this. So yeah, overall, I think we're only scratching the surface. I'm going to keep pushing in this direction a bit more, and I'm kind of excited to work on more visual and 3D design tools. I think there's a lot of interesting challenges in this space where we can apply our expertise, especially hearing the panel this afternoon. I think there's lots of interesting work that can be done. And, I always advocate that we need to move beyond one-size-fits-all approaches. We should be having not only a solid backbone when we're doing a new innovation, but also it should be informed by actual people's needs and observing them in the field, in the lab, and really trying to capture the nuances of their tasks and workflows. With that, thank you so much, and I look forward to any questions you may have.
Thank you, Carmen. We're gonna save all the questions to the very end. And so the last presentation, since we do have a little bit of time, I will quickly go through a little project I'm working on. Screen again. No. So who am I? I'm Leslie Eisted. I probably should have introduced myself at a much earlier section, but now you know who this random weird person is. I'm also here at Carleton. And I want to talk to you, as I said, about this little project that I've been working on. It's actually a aggregation of a bunch of smaller tasks about predicting success by learning from the past when it comes to making movies. So I've got two movie posters here. I don't know if you've seen both of these. Does anyone know what the big difference between these two is?
What was success? What was not?
Well, it's interesting because if you look at them, you might be thinking, oh, well, I've heard of these two movies and I know one of these is wildly successful and I'm pretty sure the other one isn't. You might be thinking to yourself that the budget on them is vastly different, except it isn't actually. John Carter was one of the biggest budget films out of Disney. I think it was out in 2012, if memory serves me, and it had a budget of over $350 million, which is approximately what they spent on Endgame. Here's the, Chris at the back says there one's a failure here. Well, was it the IMDb ratings that it failed? Yeah, that's a pretty big difference. 8.4 for Endgame and 6.6 for John Carter. This is not bad though. I mean, I think the new Snow White that's out is like 1.5. I think The Room, aside from the fan following, might be down there pretty far too. So I don't know if that's really what we mean. But this is Endgame made almost $2.8 billion worldwide. And John Carter didn't even break even. Worldwide, it only made about $284 million. But Disney dumped an insane amount of money into the production of that movie, especially if you consider that this was made in 2012 and they didn't make it back. Okay. That would have been nice if that hadn't happened, right? So it would be really nice if we knew why some productions succeed and others really fail epically. Because John Carter, by the way, is based off a book from like 1912. I think it's called like The Princess from Mars. Sounds like a pretty cool book to me. And then we have to ask the question, what does success even mean when it comes to a film? Because what we think of as success and what the studios think of success might be two very, very different things. So we could think of things as successful as being like your IMDb rating, your audience scores. What do people think of it? And if you Google for, what is the best rated movie of all time, IMDb says it's The Shawshank Redemption with 9.3 out of 10. Its audience scores. I don't know if I agree with that. It's not my favorite movie, but on average, I like this movie a lot. So that's one way we can measure success. Another way we can measure success is how many awards have you won? Oscars, people like those, right? Means you can command more money in the future and more respect in the future. If we use that as our measure of success, there are 3 movies that are tied for 11 Academy Awards, and they are Titanic, Ben-Hur, and The Return of the King. That's one way you can measure success. That's not what we mean, though. That's what we mean. We mean money. When most people, most studios are thinking about success, they're thinking about how much money did you actually bring in. So movies like Endgame and Avatar, who are constantly putting themselves back into the theaters to try to take the crown from each other again and again and again. I think both of these movies have made multi-billions of dollars. It's crazy. So we have to now ask ourselves, okay, so if that's what we're defining as success, what are things that affect the success of a movie? Yes, these are unsuccessful movies. I went and I found some of the most unsuccessful. I've heard of these movies, but I have never seen them, so I'm not going to make any comments. When we think about what might affect success, there's some obvious things like genre, the plot, the story, what actors or actresses, what talent did you bring in? I mean, if somebody brought me in to sing in a movie, that movie's going to fail epically. Even my kids don't like it when I sing to them at night because I can't sing. You got to make sure you bring in some good talent. Also, things like visual quality. Those are all obvious things that might affect the success of a movie. And if we think about it, this all makes a lot of sense. Things like certain genres perform better with certain audiences. For example, I've mentioned I have lots of kids, and with them, if I try to show them a movie like The Internship, they're going to be like, turn this off. Whereas if I try to show them anything from the Marvel Cinematic Universe, they're going to be like, yeah, this is awesome. There are certain genres that appeal to certain groups more than others. What are those trends? And is there a universal genre that seems to appeal to all audiences everywhere? I mean, when we're also talking about plots and stories, it seems obvious, but what do we mean? So we can actually analyze the plot and ask, well, what kinds of plots are people more attracted to? Is it things like rags to riches? Is it things like The Quest? What kinds of plot structures are people more attracted to? What kind of plot structures seem to perform better? When it comes to talent, when you're bringing people in, do people care about you bringing in an ensemble cast where you're like, oh, I need one of those actors and I need one of those. I need, the muscle-bound person, and I need the cute little nerd. I need this and I need that. Do you build yourself an ensemble cast? Does that perform better than a cast of, let's bring in all the big budget actors? Every one of these actors cost me $50 million. Or what if I just grabbed some local people, some new faces? These are all really interesting thoughts when it comes to how does this play a role in the success of a movie? And then, of course, you've got the obvious visual quality. Are you going to spend more money on practical effects, visual effects? How much money are you going to dump into the visual effects? Lots of those things. These are all fairly obvious contributions. But is there anything else that contributes to success? Of course there is. One of the interesting ones is release date. So this is an analysis looking at the different weeks throughout the year and what is the average box office take for that week across time. And there's this kind of phrase you see mentioned, things like January, February, March is where movies go to die. Well, if you look at the average sales, it's, it's not, movies don't tend to do too well in those weeks. But if you look as we get into summer, especially around July 4th and the end of June, you can see sales are really high as well around the end of December. So this is something we know. We know that when you release a movie can impact how much money you're going to bring in. If you think about it, let's say you've got a little indie film that you want to release and you release it on July 4th when all the big Marvel movies are coming out. You may not do very well because everybody's going to spend their $50 to go see the Marvel movie. Apparently one comes out today. And that's Fantastic Four. So you have to pay attention to when you're releasing your movie. Anything else? Well, now we start to ask some of the more interesting questions. What about the colors you're using in the movies? So does the color that you use, that palette, impact the success of the movie? We actually have done some analysis. I have a student who's actually working on this right now. And some of our early work was looking at how do we extract the color palette of a movie from its trailer, and then trying to connect that to different genres, box office sales, and so on and so forth, different eras. You've probably heard, where's all the color going from film these days? It seems like it was so colorful 50 years ago, and now everything's all bland and gray. And indeed, our analysis does show the color is leaching out of movies on average. But does the color palette impact people's perception of success? Does it impact whether they like the movie? Does it improve immersion? Does it impact the box office? These are some of the questions we're actually trying to answer. And right now we're at the stage of improving our palette extraction process. These are actually 3 palettes here. So we have Asteroid City at the top, a Wes Anderson, and the one in the middle is another Wes Anderson. Any guesses on that one? Grand Budapest. Purple's kind of give away on that one. And then the one on the bottom is one of my own favorites, which is Oh Brother, Where Art Thou? Great. So other things that we can look at when we're trying to determine what makes a movie successful. What is it about a movie that attracts the audience? We could look at things like gender and other forms of bias in the dialogue and in the cast. And we have actually been analyzing the dialogue of movies because we don't have access to the scripts. But what we do have is a data dump that was graciously donated by Open Subtitles. It's a very large database of all of the user-generated dialogue for subtitles. And we did an analysis of it looking for gender bias in the actual speaking. And then we plotted that, the bias against the box office sales. And you can see there, the red line actually shows that movies with a male bias, which for the record, that's most movies, actually typically do better than movies with a female bias, although the gap is actually closing. And the number of movies that exhibit male bias in gender, gendered language is actually decreasing. But what about things like sentiment in the plot synopsis? So if you give a plot synopsis for your marketing materials that's positive or negative, how does that impact things? And we've done some work on that as well. Don't have any plots here for it, but happy to share them at a later time. We're also looking at the trailer contents, the shot lengths in the trailer contents, because action films tend to have much shorter shot lengths in trailers, whereas dramatic films or romantic comedies have much longer ones. And actually 20th Century Fox has a predictive AI tool called Merlin, which looks at trailers, and it is trying to analyze the success of a movie based on the trailer using some of these metrics as well. We're looking at elements of stereo 3D. How does that impact success? But there's also things like the language level, i.e., are the characters using a language that's characteristic of elementary schools or college graduates? How does that impact the success of the movie? Another interesting thing in the current world situation, had been thinking about this year, this is a project that's still very much underway, is looking at things like how movie success is related to political bias and socio-political events, things like elections, wars, and environmental disasters. So we're using various AIs, some which are specially trained for political bias detection. We're also asking LLMs about themes and political bias, and trying to determine, can you detect election years through movies? Can you detect whether there has been a major event through the themes of movies that are released in certain years? And how do people like it when there is a bunch of environmental disaster movies, when there is an actual real environmental disaster movie out there, does that attract people or does that offend people? So we're looking at that. And this is an interesting word cloud that I generated. So we were generating the themes from the dialogue. And if you look at the themes of movies in 1943, you can see war, survival, loyalty, camaraderie, friendship, sacrifice. You'd expect it. It's the beginning of World War II. And then after, right at the end of the war in 1949, you can see how the themes have changed. So it's kind of an interesting analysis that we're working on. And we just got a fresh dump from Open Subtitles, so this work isn't quite ready yet. Other things we're looking at is political bias. So we looked at average box office according to the political leanings. So we've got the X's are left leaning and the circles are red, right leaning, and then the green line is just there's no political biases. And actually, there are more movies than without a bias detected than having one. But again, this is still a work in progress. So what we're really doing with this project is we're trying to identify trends. We're trying to evaluate all of the movies that have come beforehand, looking for anything that might help suggest what makes the movie successful, whether it's successful generally or successful within a particular audience. So we're collecting things like the metadata off IMDb, we're collecting subtitles from Open Subtitles, posters, trailers from YouTube, anything that's public information. And then we're analyzing that data, taking a closer look at things using facial recognition software, extracting color palettes, doing natural language processing to try to identify trends and just try to learn what is it that makes movies successful, because what we want to do is build a predictive model to try to predict box office sales or just general success from the materials that we have already. And so things like the script, the trailer, the treatment, can we actually predict what is going to improve success, what will be successful, what we need to do to make a better film? Now I'm going massively over time. But that's our goal, is to make this predictive model. But the interesting question to kind of leave you with is, if we build this predictive model like we're trying, because it's interesting, it's fun, right? If we are able to do it, is this going to create a model such that we reduce the art of filmmaking to just a formula? If you follow the formula the model gives you, do you end up with an endless stream of safe films that are boring? Would we be taking away the art by removing all the risk? Well, we're going to find out. So, all right. Thank you. I apologize for taking so much time. If there's any questions for anybody's presentation, by all means, please ask. Thank you. Anybody have any questions? For anybody? Yeah. Dinner time, right? All right. Well then, thank you everyone so much for coming. I hope it has been an informative and entertaining day for everyone. Thank you to the panelists again, students for your wonderful presentations, and my colleagues for learning more about your work. Thank you, and hope you have a great evening. Yes, thank you to Dwight as well.